AI is starting to look less like a text generator and more like a unified visual engine, one representation that can understand, generate, edit, and even reason about the future. The big shift is that these systems are moving away from fragile language-only workflows and toward discrete or latent visual spaces that actually preserve structure, identity, and motion. That matters because it means better fidelity, fewer hallucinated details, and far more efficient multimodal reasoning. What ties these breakthroughs together is a new obsession with where the model thinks not just what it says. Let's explore the first paper, ARM, an autoregressive large multimodal model with unified discrete representations. ARM, from Fudan University and ByteDance TikTok, ByteDance Seed, is an autoregressive large multimodal model that unifies image understanding, generation, and instruction-guided editing by predicting a single discrete token stream. Its key novelty is a unified visual tokenizer built on frozen SIG-LI P2SO 400M512 features and finite scalar quantization, trained with 4 complementary losses, captioning, pixel space diffusion reconstruction, sigmoid contrastive alignment, and feature distillation, so the same token space preserves both semantics and visual detail. ARM then scales a 7B Quen 2, 5 backbone on 2, 5T multimodal tokens, adds supervised fine-tuning on 0, 2 B instruction tokens, and applies GRPO with GPT-03 and GPT-4, one as reward models to align generation and editing preferences. The model reports 40.2 on MMMU, 87.3 on POPE, 0.86 on GenEvol, 0.56 on WISE after RL, and 6.68 on gedit bench EN-GO, while its RL stage produces clear cross-task synergy. WISE rises from 0.5 to 0.56, and gedit bench EN-GO from 5.75 to 6.68 without degrading understanding. The tokenizer ablation also shows why the design matters. Adding semantic and feature regularization lifts ImageNet zero-shot accuracy from 0.2 to 80.2 and PSNR from 15.2 to 19.6, indicating that discrete representations can support both recognition and high-fidelity synthesis in one autoregressive framework. Let's explore the second paper. HydraX, native unified multimodal models with holistic visual tokenizers. HydraX from Nanjing University, Cassia, Tencent Hunyuan, and Shanghai AI Lab is presented as the first native unified multimodal model to unify image and video tokenization inside a single vision transformer, building on the earlier Hydra framework and Quen 2, 5, 7B instruct. Its tokenizer, Hydra XTalk, uses a counterintuitive but effective recipe: frame-level causal tubelet attention instead of full spatiotemporal attention, hierarchical 2x2 temporal patchify instead of one-step 4x compression, and a lightweight decompressor that restores compressed video latents for dual supervision from SIGLIP, SO400M, Patch16, Naflex, and Intern Video NextL. On reconstruction, the tokenizer reaches 32.04 PSNR on ImageNet, 28.19 PSNR on Davis, and 36.88 PSNR on UCF, while the fully trained 7B model improves over SHO2 on video generation vbench by plus 1.87 QS, 3,26 SS, and 22,8 fem total. For image understanding, it posts 86.5 on AI2D and 2,350 on MME. For video understanding, it scores 59.1 on MVbench and 60 on video MME. The paper also shows that moving source-target interaction for image editing into the tokenizer rather than the LLM raises IMG edit bench overall from 2.8 to 3.2 and source reconstruction PSNR from 20.74 to 27.65, confirming that latent level coupling is crucial for identity-faithful edits. Let's explore the third paper. Imagine before you predict interleaved latent visual reasoning for video event prediction. Imagine before you predict. Interleaved latent visual reasoning for video event prediction, developed by Shanghai AI Laboratory collaborators with universities including USTC, proposes Future L1, a Quen 3, VL, 8B based multimodal framework that alternates between text tokens and continuous latent visual spans instead of translating every future hypothesis into language. The core idea is to preserve dynamic future semantics in latent space for video event prediction. Then train that behavior in 2 stages. Supervised fine-tuning on FUTUREL 150K, a 50K subset curated from TWIFF, 7M by selecting samples where intermediate future frames provide measurable visual gain, and LA-DAPO reinforcement learning, which adds outcome contrastive and temporal diversity rewards to optimize sampled latent trajectories. On FutureBench, Future, L1 lifts Quen3, VL 8B from 61 to 73.2 after SFT, and to 85.4 after RL, surpassing video CoE by 10.4 points. On TWIFF Bench, it raises the average score from 2.44 to 3.04. The ablations show the latent MSE weight of 0.1 and latent budget 4 are optimal in SFT, and the best RL coefficients are 0.2 for outcome contrastive reward and 0.1 for temporal diversity. The paper also reports that Future L1 RL uses 195.3 tokens and 0.91 seconds per sample on FutureBench, indicating that its accuracy gains come with more compact inference than text-heavy multi-turn video reasoning. That's a wrap on today's AI paper highlights. Thanks for watching.